Hi. In our last few videos, we looked at how to calculate future value of a lump sum given the present value, the interest rate per compounding period, and the number of compounding periods. Now we're going to see how to find the present value, how to find the interest rate per compounding period, and how to find the number of compounding periods. So let's go to our whiteboard and let's remind ourselves that we have this formula: future value is equal to present value times 1 plus r to the t. Okay. So we know how to find future value. Well, we can rearrange this formula to solve for the present value, to solve for r, or to solve for t. Let's do the one that we use most frequently first, and that is to solve for present value. So we can say that present value is equal to the future value divided by 1 plus r to the t. Now, this is the way we're going to do it, and this is the way your textbook does it as well. But I want to let you know that some books and some other people do it a little bit differently. Not much, but they do it just a little bit differently. They simply say that the present value is equal to the future value times 1 over 1 plus r to the t. Okay, there. And what they do is they call what is in the bracket here the discount factor, or the present value discount factor. Now, mathematically, it's the same thing. You take the future value, divide by 1 plus r to the t, is the same thing as taking the future value and multiplying it by 1 over 1 plus r to the t. But some people like to multiply more than they like to divide, so they do it this way. We're not going to be doing it this way. It's perfectly fine. I got no problems if you do it that way, but that's not going to be the way I'll be doing it. But I wanted you to recognize it because other people do it that way. So if you say, I'm finding the present value by taking the future value and multiplying it by something, okay, well, what they're multiplying it by is this right over there, 1 over 1 plus r to the t. Well, let's take an example here. Let's suppose we need to have $500 in 2 years. So here's time 0, which is today. Here's time 1, and here's time 2. So I need $500 in 2 years. And suppose that interest rates are 7% with annual compounding. So it's 7% annual interest rate with annual compounding. So the question is, how much money do I need today so that it will grow and become $500 in 2 years? In other words, what do I need today? What's the present value so that it will grow at 7% for 1 year? And then that number will grow at 7% for a second year and turn into exactly $500. Well, that's finding the present value of $500 to be received 2 years from now when we have annual compounding at a rate of 7%. Sometimes it's called the discounted value, and the 7% might be called the discount rate. You'll hear that term referred to a lot. Whenever you hear that term discounting, it's taking something from the future and finding out what the present value is. So to do this, we're just going to say present value is equal to $500 divided by 1.07 raised to the second power. That's the math that we're doing. But like before, we're going to go to Excel to actually solve the math problem for us. But we need to know what is the math problem that Excel is solving. Okay. So let's go to Excel here. Here we go. And we're going to type in equals PV to find the present value, put my bracket up there, go to my function wizard, and the function wizard wants to know what's the rate. That's the interest rate per compounding period. In this example, that's 0.07. What's the number of compounding periods? NPER is 2. And my future value, same way as before. If I put it in as a positive, my answer will be a negative. If I put it as a negative, my answer will be a positive. So let's just type it in as a positive number here, okay? That's telling Excel that that's going to be a cash outflow in 2 years of $500. So Excel is going to say, okay, here's what you need as a cash inflow today so that you can have a cash outflow of $500 in 2 years. And Excel says the answer is $436.72. So that if I have $436.72 today, it will grow and become $500 in 2 years. So we can see that if we take a look at our class notes here, that rather than me writing it up on the whiteboard, that if I took 436.72 today and I invested it at 7%, 436.72 times 1.07 is $467.29. So this number is 7% more than this number is. Now this times 1.07 gives me exactly $500. So this times 1.07 gives me this, and that times 1.07 gives me that. Or we can say this times 1.07 squared gives me this, which is what we're doing here when we say 500 divided by 1.07 squared gives me the 436.72. So if I want to have $500 in 2 years, I need to invest $436.72 today if I have annual compounding at 7% for 2 years. Okay, let's do another example. Let's suppose I want to have $50,000 in 10 years and the interest rate is 9%. How much do I need? In other words, what is the present value of $50,000 to be received 10 years from today if we have at 9% is the interest rate? But let's put a little twist in there. Let's just say 9% is the APR and we have monthly compounding. So here's the situation. Here's time 0 and here is 30 years from today. I'm sorry, 10 years from today. Now, 10 years is going to be how many months? It's going to be 120 months, isn't it? So I want to have $50,000 out here. And the APR is equal to 10%, right? I'm sorry, the APR is equal to 9% there. So the monthly rate is equal to 0.09 divided by 12. Now I know that's 0.75%, right? 9% divided by 12 is 0.75%. So that is my true interest rate. Because I have monthly compounding here, the true interest rate is a monthly rate, 0.75%. I'm just going to write it as 0.09 divided by 12. But hey, you can write it as 0.75%, and that's fine. No problems with that at all. So we're going to say present value is equal to the future value divided by 1 plus r to the t. Present value is equal to $50,000 divided by 1 plus 0.09 divided by 12. That's my monthly rate raised to the number of months, 120th power. You have to do months on this. If you do it with years, you're going to get the wrong answer, okay? Because we have compounding every single month. We don't have compounding just at the end of every 12 months, okay? So we've got 120 different times my money is growing, and we need it to eventually end up or exactly at 120 months, get to $50,000. So what do I need today, okay, to deposit so that it'll grow that way? That's what this is solving right there, okay? So if this is a 10-point problem, there is 9 of the points telling me right there. That tells me you understand everything. It tells me you understand you're solving for present value. It tells me you're understanding that it's monthly compounding. You know what the monthly rate is. You know how many months it is. And you know exactly what Excel is doing to solve the problem. After that, it's pretty easy. You just plug the numbers into Excel, and if you don't make any stupid mistakes, then you get the last point as well. But this part of it right there, that is worth 9 out of the 10 points. Getting the right answer is the 10th point. Because what's important is not getting the right answer, believe it or not, because it's a made up problem. Okay. You don't really, I really don't know anybody who is expecting to get $50,000 in 10 years and wants to know how much they deposit today. Okay. I just made it up. So getting the wrong answer is not going to hurt anything because it's a fictitious problem. But what is important is that you learn how to get it. So when it's not a fictitious problem, when it's something that really matters for you personally or at work, that you will know how to do it. So this is all about learning how to do it and not just getting the right answer. But I like to see you get the right answer. So we have an extra point in there for that. Okay, so let's go up to Excel. And in Excel, we're going to use our present value function again. So we're going to say equals PV for present value, put the bracket in there, and we're going to say my rate. And again, it has to be the monthly rate. So that's going to be 0.09 divided by 12, or you could type in 0.75%. That would work. The number of periods, you can do either 10 times 12, that'll work, or you can just do 120, but it's got to be the number of months because we have monthly compounding. The future value is 50,000. If I type that in as a positive, my answer will be a negative. If I type it in as a negative, my answer will be a positive. Cash inflows and cash outflows. So I hit OK, and it says that I need today $20,396.87. That if I have that today, it will grow and become $50,000 in 10 years. So the discounted value of $50,000 to be received 10 years from now is $20,396.87 when the discount rate is a 9% APR with monthly compounding. So right now we've got two equations that we have learned about, right? Let's go back to the whiteboard. We have that the future value is equal to the present value times 1 plus r to the t. And we have that the present value is future value divided by 1 plus r to the t. Well, what happens if we want to solve for r? Okay. Now, if we want to rearrange the equation to solve for r, and you don't have to be able to do this, but hey, it's right there in your notes to be able to see how to do it if you want to do it. But if you want to rearrange that equation, let's go to the notes so that you can see that. If we go to the notes, we're going to see that it's going to be R, which is my interest rate per compounding period, is going to be equal to the future value over the present value raised to the 1 over t power, where t is my number of compounding periods, minus 1. So again, that's just rearranging either equation 1 or equation 2 to get r over on the left-hand side there. So let's see what kind of a problem we might run into where we need to solve for r. So let's go back over to our whiteboard, get a clean whiteboard, and let's suppose that someone tells you that if you give them $100 today, they'll give you $120 in 3 years. So here's time 0, time 1, time 2, and there is 3 years. So you surrender $100 today. So we'll put a little minus sign in there to remind us that this $100 is a cash outflow today. And you're going to get $120 in 3 years. Now, the question is that a good deal or is that a bad deal? Now, personally, I can't just look at that and say, oh, that's a great deal or it's a terrible deal. I don't know. The only way I can tell if that is a good investment or a bad investment is to figure out what is the interest rate. There is some sort of an interest rate that will turn $100 today into $120 in 3 years. I want to solve for what that is. Okay. So what am I going to do? There's 2 ways you can solve this really. Okay. I'm just going to give you the same answer, but there's 2 ways you can set it up. One is you can do just what we saw before. R is equal to the future value over the present value raised to the 1 over t power minus 1. And if you do that, the future value is 120. Do not put a minus sign by the present value. That's just to tell us it's a cash outflow over 100. Okay, raised to the 1 over t power. Now, here we have to decide what are our compounding periods. I said it's 3 years, but we never said where the compounding is in here. Okay, so the natural way to do this is to say it's annual compounding. So we're going to do it that way, but it didn't have to be. I could have said semi-annual compounding or set up for monthly compounding or something like that. Okay, so anyway, 1 over t, t is the number of compounding periods. So the number of compoundings is periods is 3 minus 1. So I'm going to ask Excel to do that math problem for me. Okay, now there's another way we can set it up, and this is perfectly acceptable. We can do it this way. We can say present value equals future value divided by 1 plus r to the t. That's fine also. And my present value was 100. That's equal to 120 divided by 1 plus r. R is what we're solving for, to the third power. Now, the difference is here we're saying r equals this. So we can now say r equals and then get our answer. Here we're saying 100 equals this. So we can't say equals and then put our answer, because we can't say 100 equals whatever this interest rate is. We have to say R equals, and then we put our answer there. Okay, so that's very important. It really is. You don't want to say 100 equals 5% or something like that, because that would be pretty silly, right? But here you can say R equals 5%, if that was what your answer was. I don't think that's what our answer is. So let's go into Excel to get the answer for this, okay? Go back over to Excel here. And as you probably remember from before, that we are going to use the rate function. So we're going to say equals RATE to solve for the interest rate. So we hit our bracket there, go to my function wizard, and we want the number of periods. First of all, we already decided we're going to do annual compounding, so it's 3 periods. Then we type in the present value. Present value was 100. Type in the future value was 120. And I'm deliberately making a mistake here, by the way. I hit OK, and Excel is yelling at me. Exclamation mark, hashtag NUM, exclamation mark. That is Excel's way of saying, hey, you dummy, you did this wrong. And when you get something like this, it typically means you messed up on the signs. And we did here, okay? How do we mess up on the signs? Well, we put in the present value as a positive and the future value as a positive. And Excel says there's no interest rate that works that way if you are receiving $100 and then 3 years later you're receiving $120. You have to have both a cash outflow and a cash inflow. Now, as it turns out, it doesn't matter which one you make a negative, but you need to make one of them a negative, okay? But you're going to get the same answer either way. I'm going to turn the present value into a negative because that's the way I had first written it up, that you're giving somebody $100 today, and 3 years later, they're giving you $120. Now Excel says, hey, we can find the answer for this. So we click OK, and we get the answer of 6%. And that's kind of right, but it's not good enough. The reason why it's not good enough is because Excel, by default, rounds percentages to the nearest integer, the nearest percent, 6%. We want to be more precise than that. We could take it out a lot of different decimal places, but in finance, it's standard practice to take out percentages to the nearest basis point, BASIS point, POINT. A basis point is 1/100th of a percent. And that is the standard way we do things in finance, is we express things to the nearest 1/100th of a percent. So we're going to go up here to home, And we're going to move the decimal over a couple of places to 6.27%. And there's a big difference between 6% and 6.27%. Now, 6.27 does round to 6%, okay, but we're not going to do that, okay? We're going to, it's actually, there's even more out there, but this is, you can take it out a lot of different, a lot of more decimal places, but it is okay to round to the nearest basis point. Again, that's the standard practice in finance. So we know there's more decimals, and if we had more work to do, we would keep those in Excel and do cell referencing. We'll talk about that later, but it's okay to round this to 6.27%. So we're going to say that that is our answer. So let's go back to our whiteboard here. And we're going to say, okay, here R is equal to all of this, and Excel just did that math problem, and it ended up getting 6.27%. And it's okay to say that that is 0.0627, but you don't say it's 0.06 or 6%. That is too much rounding, okay? So we take things to the nearest basis point, 6.27%. Or you can do this here, okay? If you do this particular problem, solving for R, you say R equals 6.27%. But do not say that 100 equals 6.27%. That'd be pretty silly to say 100 is equal to 6.27%, okay? And you won't look like you're a graduate student who took some finance courses there. So we don't want to do that, okay? We want to say R equals 6.27%. All right, so we know how to solve for R. We're solving for, you're using the rate function in Excel. Now we want to be able to solve for T. So let's do the following. Or first of all, let's see what T is going to look like. If I want to get T by itself, it's going to be equal to the natural log of the future value divided by the present value divided by the natural log of 1 plus R. Now, actually, this will work if you do common logs or natural logs, okay? But in finance, we tend to use natural logs. Now, why did we have to use logs? Because T was an exponent. So to get T down from its perched position as an exponent, we needed to take the log of each side to do it. You do not need to know that. You do not need to memorize this formula or anything like that. But hey, some of you all are engineers, I know, and you'll get very upset if I don't show you how we derived a formula. But it's so we're gonna end up solving a problem with this, or it's perfectly acceptable as far as I'm concerned to say again, present value equals future value divided by 1 plus R to the T, and then you say T equals. Let's see what T ends up equaling there. So here's our problem that we're going to take a look at, okay? The problem is I'm going to invest some money today at time 0. I'm going to invest $1,000. And my goal is for this money to grow and become $100,000, okay? And it's going to be earning interest at a rate of 14% per year. That's with annual compounding. So the question is, how long is it going to take for my money to grow from $1,000 to $100,000 if it's growing at 14% per year with annual compounding? Well, we're going to use these formulas right there. Okay, if we use the one on the left, we're going to simply say that T is going to be equal to the natural log of $100,000 over $1,000 divided by the natural log of 1.14. Right? That's I want to solve. That'll give me that'll solve this problem. Or I could say present value, which was $1,000, is equal to future value $100,000 divided by 1 plus R, which is going to be 1.14 raised to the T power. T is my unknown. We're solving for T. Okay, either way is okay to set this up, except I hope you wouldn't cross things out there like I did. All right, so we're going to go into Excel now. And if we go into Excel, we're going to be using the function for, we're going to use the function for NPER equals NPER for number of periods. Okay. And go to the function wizard, and our rate per compounding period is 14%. Our present value and future value need to be opposite signs again. One needs to be a negative, one is a positive. So we'll say present value is $1,000. That's what I deposit into my savings account. And then I want the future value to be 100,000, and I want to receive that from the savings account. So it won't work unless they're opposite signs. It doesn't matter which one is a negative, what one of them needs to be. And we ask Excel to solve this, and Excel comes up with an answer of 35.14639. And unfortunately, that's wrong, okay? And here's where we got to remember that you and Excel are a team, and you are the brains. Excel is merely the muscle. Here's what Excel did to get 35.14639. So we need to understand why Excel gave us the wrong answer here, because there's always a reason for it. Excel solved this problem right there. Excel did the math on that. And the math on that is, in fact, 35.146, okay? But the answer isn't 35.146 because we have annual compounding. Now, as it turns out, at the end of year 35, you have $98,100 approximately, okay? And at 35.146 years, you don't have $100,000 because you don't get any more interest until year time 36 out here, remember? Because we have annual compounding. So we have $98,100 after 35 years. This entire year, we have $98,100. And then we earn some interest at time 36, and it takes us way past $100,000. I don't remember exactly what the number is, but it takes us well past $100,000. So we never have exactly $100,000 in our account. But when do we have at least $100,000? It's at time 36. So in order to understand what is going on, okay, the math on this, okay, does in fact equal 35.146, because Excel doesn't know we've got annual compounding. Excel is just solving the math problem that we gave it. That's why you kind of have to understand what Excel is doing, okay? But we know we have annual compounding, and it's not until we earn our interest at the end of the 36th year that we will have $100,000, and we'll have more than $100,000 at that point in time. So again, it's important to understand what Excel is doing, and you can't just plug numbers in and say, I get the answer. I don't know why I get the answer, but that's what Excel is telling me. You're the brains. Excel works for you. It's the hired hand that is the muscle, and just does these math problems faster than what you can do. So we have learned now how to find present value. We've learned how to find future value. We've learned how to find R, the interest rate per compounding period. And we've learned how to find T, the number of compounding periods. So in order to find any one of these, you have to know the other three. All of these are with single lump sums. In other words, there's just one present value, one future value. What we're going to do next in the next video is we're going to talk about a series of cash flows where you're getting money at time 1, time 2, time 3, time 4, etc., and how we handle that. So we're in good shape now in terms of individual cash flows. Next time we get together, it'll be a series of cash flows.